We're talking latching load switch right here. This is a very useful circuit to enable your circuitry only when a button is pressed, and then whatever controlling logic you have on the other end, either a microcontroller or maybe even a timer circuit, you can use that to shut off all your circuitry and draw nearly zero power, zero current. I'm just going to briefly discuss how this guy works, then we're going to go into building it and simulating it. So what you have here is just a battery. This battery, if you're using lithium ion, you're going to be going from around 3.1 to 4.4. I'm just leaving at the higher point here. Now this guy is going to be charging up this guy. Along with this guy, as there is no current flow, this guy is also going to be getting charged up to this level along with this guy. There's no connection here, and this guy on the other end is being drawn to ground. Because there is no current flow, this guy is being held at ground, and this guy is going to be held at the battery voltage. This is very useful in about 2 seconds, or 0.25 in our case, when the switch goes on. When this switch turns on, a bunch of stuff happens. We have this voltage potential here. We have this charge in this capacitor. You're going to be transferring that to the gate of this end FET. That is for a minute amount of time is going to charge up this FET, and it's actually going to turn it on. That's going to pull this guy low. That's going to turn this guy on. This guy, this side is going to become the same voltage as this guy, and because we have it's essentially just a large voltage divider, because we have more voltage here now to go across this resistor, it's going to keep this guy latched on. Perfect. It's what we expect. We want this thing, we want the switch to turn it on, keep it on. We can actually deactivate this guy, and it won't change the state of this latching circuit. Now, if we hit it again, what's going to happen here is we have this gate voltage charging this cap to the point where this gate voltage goes below threshold. It turns off, which gives this guy enough time to charge up this gate, which then turns this off. You let go of that, everything goes back to a steady state. This is off. It's ready to be turned on again by another switch press. So the circuit does have a limit, though. You can't press this too fast. You actually need the time to charge and discharge this capacitor. And that's all limited by these R's and the C, obviously. So I'm going to be going into how to build this guy in Cadence PSpice. We're going to simulate it in 3 different ways. You guys, if you feel like playing, go for it. Change it up. Whatever you need to do to make this circuit yours. Here we go. First thing you want to do here is create a new project. You want to make sure it's an analog mixed project. That way you can actually do the simulations. So you want to open up that page, and then where we want to start dropping with is the ground. Ground is important. It's an important reference. It's going to be used throughout the design here. And now what I'm doing here is I'm actually dropping some of the important components. So we're talking about power supplies, we're talking about resistors. In this case, I'm going to be dropping that power supply, setting it 4.4 volts. That's pretty much the maximum I would expect from maybe a lithium-ion battery. And as you can see, I'm using the search function here that can be used to call out particular components. In this case, I'm using some small signal transistors. These guys are going to be forming the basis of our load switch. Next step is to grab one of these switches here. It's actually kind of a cool functionality in the way you can simulate here in PSpice. You can actually set some really interesting parameters for switches, but also you can configure some voltage controlled switches, which you will see shortly. Now I'm setting the values of these passives. I'm pretty much setting them to what I had done earlier, what I saw that had worked. You guys are more than welcome to play around with the values, see what happens to the simulations when you change the values. Next part is, or at least don't neglect this part, because your simulations will not work. You have to attach the library, the simulation library, to the actual simulation configuration. So I'm showing you the screen. I'm actually navigating to the library for both of these parts. Both of these parts are in the same library. They're in the Infineon library. You can navigate to it through your C drive all the way through the cadence directories, PSpice library, and then you just add it to this project, add it to this design. When you go to run the simulation, it'll actually work. Next up, we just want to drop some of these voltage probes to all the junctions that we're most interested in. Then when we actually hit the simulate button, we'll have some nice waveforms. Next step is to actually set the time duration of these simulations. I'm just going to be setting it to 1 second as a general simulation. It's going to pop up, it's going to give us all the waveforms shortly. So it's right around here where I realized the simulation is not what I expect it to be. I wonder if you guys can spot it right now as a problem with the transistors. Turns out I had totally flipped the drain and the source of the transistors, so I'm not getting the expected outcome here. You can see the yellow line, which is the output of this load switch, is just staying on the whole time because the body diode of that transistor is completely reversed. Same thing with the NFET here. We'll see in a second. It's still the same because, oh look, that guy is always on as well. Got to flip that NFET around and we'll be good to go. Now that we rerun the simulation here, you can see that the output of this load switch configuration is working. It's going from an on position to an off position when the switch is activated at around 0.25 seconds, a quarter of a second. You can see all the waveforms changing appropriately. This is awesome. Next step is what we're going to do is we're going to hook up a voltage controlled switch and we're going to toggle it on and off just so you see what the waveforms look like during the transitions from on to off and off to on. So getting to this voltage controlled source is the same way you would get to the other type of switch as the regular switch. I'm setting the on voltage for this guy to be around 2 volts. The off voltage is going to stay at 0. That part is important because the supply that I'm going to be using is a pulse supply. I'm going to be pulsing it from 0 to 2, which is the same control voltages as the switch. Now I'm setting the values of the voltages. V0, V2 are just the transition to the steady states. TD here is 0.4, that is the time delay. Rise time and fall time are just going to be set to 0. No reason to change that for now. Finally, I'm setting the pulse width, which is just going to be set for 5 nanoseconds, and the period. So I want this to be happening about every 2 seconds. I am going to speed it up very shortly just to show what happens within the 2-second time span when we're switching it on and off much faster. Setting up the rest of the circuit and then we'll get into the simulation. Next step is actually to change. I originally put in a period of 2 seconds, but we actually want it to be much faster. Changing it to 0.5 will actually have a second transition down to 0.9 seconds. I'm going to tweak this value a couple more times just so I can see multiple transitions happening in this simulation time frame. The waveforms here are interesting. It's cool to see the sawtooth pattern on the red waveform. That is the junction point at the cap there and the switch. That is the voltage that is important to the gate on that end FET. You can also see a very clean transition for the yellow lines. Those are going to be the on and off of the output of this load switch. Next step is going to be adding an additional end FET. This end FET is going to be set on the gate of the other end FET that's controlling the P FET of the switch. This guy is essentially going to be controlled either by an external timing circuit or by a microcontroller. This is going to give the code or whatever you want in the circuit to turn it off on demand without having someone to press the button. This is useful for someone to turn it on. Great, it's on, it's running, it's logic, and then it turns off. I'm switching all the pulse circuitry to this FET because what I'm going to be doing is setting that normal switch above there to turn everything on, and then I'm going to be setting this pulse to turn it off. I'm using the pulse because it'll kind of represent what happens with a microcontroller. Microcontroller turns on its output to control this FET to turn everything off, but it will only be there for a short amount of time because essentially we're pulling the rug out underneath this microcontroller. This microcontroller is just about to lose power. Before simulation here, I am going to be adding a pull down to the gate of that third end FET. That way this guy is going to be at a steady state when off. It's not going to be floating. In the real world, that's very important. In simulation, most likely it would be held at a certain state just because it's not really going to be able to just simulate what state or what floating point that gate is going to be at. Once I have the second switch set up, we're going to run the simulation. You're going to see what happens. Just about to run the final simulation here. Just about what I expect. It's turning on when we want it to, and it's turning off when we want it to. If you look at the blue waveform, you can see that it's turning on for a very short amount of time, which gives this new end FET the charge that it needs to turn or pull down the kind of the purple, the gate of the other end FET. We're just about done here. You guys can get the source files for the schematic for the simulations on the website. So check out the link below, leave a comment, let me know how it goes, and we'll see you at the next one.